Okay, so in this video, what we are going to do is study what is an important question in analysis, that is when is the interchange of limits and integrals permissible. Okay, so the basic question is as I've written here. Suppose you have a sequence of functions fn of x which converges to some limit f, let's say. The question is, when can you justify that limit n tends to infinity of the integral of fn is in fact the integral of the limit, let's say f, right? In other words, when can the limit and the integral be interchanged, right? So this is the basic question we are going to talk about in this video. We actually already know a few cases where this is possible. Okay, so first we know that if fn converges to f uniformly, so uniformly, and fn is continuous, okay, in that case this holds. We have already proved this. It's actually fairly straightforward, right? Uniform convergence plus continuity is sufficient. Right? Another condition, it turns out, which is more general than the previous, is that fn converges to f uniformly and fn is Riemann integrable. Okay, again for all n. Right? Why is this more general? Because continuity implies Riemann integrability, right? So it's a weaker assumption to simply assume that fn is Riemann integrable than it is to assume that it is continuous. So if you have uniform convergence, right, then even Riemann integrability of the sequence of functions implies in fact not only the Riemann integrability of the limit, but also that the limit of the integrals is equal to the integral of the limit, right? So this latter statement can be proved along very similar lines to the former. So I'm going to leave this as an exercise to you, right? The first one is something that we've already proved. The second, it turns out, is is again an easy extension of the previous result. Okay, so in both of these we see that if you have uniform, and see, mind you, the Riemann integrability of fn is required in any case for the left hand side in the here to be well defined in the first place, right? So you couldn't expect for anything weaker than the second statement, so long as you have uniform convergence, right? So uniform convergence essentially allows you to make this interchange work, right? That's the moral of the story so far. So the real question we are going to be asking here is, what if we don't have uniform convergence? In other words, what if we only have pointwise convergence? Right? So in this case, well, under what conditions can one argue that in fact the interchange of the limit and the integral is valid? Okay. Now it turns out that the first thing to note is that when you only have pointwise convergence, f need not even be integrable. Right? Even though all the fn's are integrable. Like if you look at the result that we wrote out here, right, the second condition that we wrote here, well, if you have uniform convergence of a sequence of integrable functions, then the limit is guaranteed to be integrable. However, it turns out that if you have pointwise convergence of a sequence of integrable functions, the limit itself may not even be integrable. So far from the interchange, the right hand side that we have written up here may not even be well defined. Okay, let's give one example that demonstrates this. The example we will construct will have the limit function be defined as follows. So f, let's say, goes from 0 through 1 to r, is such that f of x equals 1 for rational x and 0 for irrational x. Okay, now how do I construct a sequence of integrable functions that converges to x? Let xk, the sequence xk, be an enumeration of the rationals between 0 and 1. Right? In that case, I define fn as follows. Fn is equal to, let's say, 1 for x equals x1, x2, all the way up to xn, and 0 everywhere else. Right? Another way of seeing or writing the same function fn is to think of it as a sum of indicators. So you have summation j running from 1 through n of the indicator of xj. Right? What do I mean by that? That is, this indicator function takes the value 1 at xj and 0 everywhere else. Right? So it's the sum of the first n of these indicator functions. Okay. Now the thing to note is that fn is integrable, right? That's not difficult to see. In fact, it has an integral of 0. So the point is that fn is integrable for all n, right? I also leave it to you to check that fn converges to f pointwise. Okay, but f is not integrable. Right? So the first thing we have noted so far is that while uniform convergence implies the integrability of the limit so long as the sequence of functions is integrable, pointwise convergence does not offer such a guarantee. You can have a sequence of integrable functions which converge pointwise to a limit which is not even integrable, right? Moreover, if all you have is pointwise convergence, it turns out that even if the limit is integrable, it turns out that the interchange may not be valid. Okay, so let me give one example that illustrates that as well. Okay, example. So I'm not going to write down the functions fn. What I'm going to do is just sketch them. So this is x. Okay, fn is going to have a triangular curve. So fn of x looks like this. It's a triangle between 0 and 1 and 2 by n. Okay, and goes like this. Okay, and the height of this rectangle, so this is at 1 by n, the height is n. Okay, so the way I want you to think of fn of x is that it is a it's 0 everywhere else, right? It is a triangle between 0 and 2 by n, the curve, and it has a height it has a height of n. Okay, it's an isosceles triangle, in which case you can check that the area under the curve is in fact 1 for all n, right? Because as n increases, this left point actually will shrink down to 0, but the height goes up in such a way that the area under the curve remains preserved. Okay, so that is the way fn is defined. Okay, so fn, all of them, let's say, can be thought of as mapping 0 to 2, right? For n equals 1, it would be 2 to r. Okay, defined as follows. Now, what I'd like you to convince yourself of is that fn in fact does converge to 0 pointwise. right? Because fn of 0 is of course 0 for all n. Fn of x for any x which is not 0 will in fact become 0 for n large enough. So fn of x is equal to 0 for large enough n, and so therefore fn converges to 0 pointwise, right? But the integral of fn of x equals 1 for all n, right? So trivially the limit of the integrals is 1, however that is not the same as the integral of the limit, right? Because the integral of the limit is 0. Yeah. So that's another example where if you have pointwise convergence, first we had one example that said that the limit itself need not be integrable in spite of the fact that the sequence is integrable. Even as this example illustrates, if the limit is integrable, the interchange may still not be valid. Okay, so what we are going to do is now state two very important results which give you sufficient conditions for the interchange to apply in the context of pointwise convergence. Okay, and these results are very important in analysis. They are called the dominated convergence theorem and the monotone convergence theorem. So we are not going to go through the proofs of these. I'm just going to state them and then we'll interpret them. So dominated convergence theorem. Okay, suppose that fn is a sequence of integrable functions on AB and fn converges to f pointwise where f is integrable. Right? We need this additional, we have to impose the condition that f is integrable because we know that the pointwise limit of a sequence of integrable functions need not be integrable, right? Now in addition, suppose that there exists some constant m greater than 0 such that fn of x is in fact less than equal to m for all n and x. Okay, in that case, so that you have to be able to find a suitably large constant m such that every function in absolute value is upper bounded by this m. Okay, in this case, indeed, limit as n goes to infinity of the integral of fn of x is in fact equal to the integral of f. Okay, so this is the statement of the dominated convergence theorem. If you are able to produce such a constant m, which for across the sequence is basically an upper bound on the absolute value of the functions, then in fact the limit of the integrals is equal to the integral of the limit. Okay, so this is one important statement. So again, I'm not going to go through the proof of this. What I will instead do is provide a reference to a proof of this, which in fact uses nothing more than the machinery that we have already built in the course. So usually the dominated convergence theorem is proved in a much more general context, specifically in the context of the Lebesgue integral in more advanced courses. However, as stated here, this version of the dominated convergence theorem can in fact be proved using elementary techniques as well, right? And a one-page proof of this is something that I will make available for those of you who are interested, right? Another statement is going to be the monotone convergence theorem. right? So the monotone convergence theorem goes as follows. Suppose again that Fn is a sequence of functions that are integrable and that Fn converges to F pointwise, where F is also integrable. That are integrable, let's say, on the interval AB, and Fn converges to F pointwise, where F is integrable. Okay, now suppose that you have monotonicity. Now suppose that f1 of x is less than equal to f2 of x for all x, which means that this is a sequence of monotone increasing functions, right? There's a pointwise monotonicity across these functions. Suppose this is also true, then in fact the interchange of the limit and the integral holds. For all x, well, of course in AB, then limit as n goes to infinity is equal to okay. So we have given two conditions. The dominated convergence theorem, where in addition, so the basic part of the first part of the hypothesis is common. You have a sequence of functions which are firstly integrable themselves, right, on a certain interval AB, and moreover you have pointwise convergence also to an integrable limit, right? In the case of the dominated convergence theorem, in addition, one assumes that one can find a positive constant such that the functions are all upper bounded in absolute value by m over the interval a to b. In that case, the interchange between the limit and the integral is valid. In the case of the monotone convergence theorem, instead one assumes that the sequence of functions itself is monotone increasing. That is, for every x, if you look at the sequence fn of x, that is in fact a monotone increasing sequence. Okay, then in fact the limit and the integral can be interchanged. Now, one thing to note is that in the limited context of the Riemann integral that we have actually been discussing, the monotone convergence theorem is in fact a corollary of the dominated convergence theorem. So in this case, the DCT in fact implies the MCT. Okay, why is that? Well, think about it. The fact that f is integrable implies that f is bounded. So therefore, under the hypothesis of the monotone convergence theorem, there in fact does exist a large enough positive number, capital M, that satisfies the hypothesis of the dominated convergence theorem. Okay, so in the limited context of the Riemann integral that we are working with, the monotone convergence theorem can be thought of as a corollary of the dominated convergence theorem. However, it turns out that in more abstract spaces, and specifically in the context of the Lebesgue integral, the monotone convergence theorem is in fact an independent statement which is not a consequence of the dominated convergence theorem. And in particular, this follows from the fact that in more general contexts, integrability does not imply boundedness. You can have integrable functions which are not bounded, and so the monotonicity and the integrability of the limit does not imply directly that you can find an upper bound of the form m in the statement of the dominated convergence theorem. Okay, so these are two important results that essentially allow you to interchange the limit and the integral when all you have is pointwise convergence. Okay, so we'll stop here and talk next about the fundamental theorem of calculus.